Okay, good morning. We have discussed the concepts related to vapor absorption refrigeration system, particularly how to calculate the properties of mixture for different processes using the enthalpy composition diagram that we have seen in the previous lectures. Okay, now we will try to see one numerical problem on the concept of vapor absorption refrigeration system. Okay, if you recall my very first lecture, there I have given you the general layout of the vapor absorption refrigeration system, which includes condenser, expansion device, evaporator, and then the compressor of VCRS is replaced with absorber, pump, generator, and expansion. Okay, and even in the previous general layout, I had also given one preheater, but for this numerical problem, we will not at the moment consider preheater. In first part, in second part, we will try to include preheater as well. Is this one clear? Now, you can see that in condenser, QC amount of heat is going out at temperature TC. In generator, QG amount of heat is added at temperature TG. In absorber, QA amount of heat is going out at temperature TA. And usually, if the ambient water we are using for cooling both the condenser and the absorber, then TA will become equal to TC. Okay, and in evaporator, QE amount of heat is added to the refrigerant at temperature T. Now you can see different state points also I have designated over here. For example, state 1 is exit of absorber and inlet to the pump. Okay. State 2 dash is exit of pump. State 2 is exit of generator and inlet to expansion valve. And then after this, let's consider some state 2 double dash over here as inlet to absorber, and then state 3 is exit to generator and inlet to condenser. State 4 is exit condenser and inlet of expansion valve, and state 5 is inlet to the evaporator, and 6 is exit of evaporator. Okay. Now one table is provided. In this table, corresponding to different state points, what are the values of pressure and temperature? These are also given. Okay, so you can note down the values of pressure and temperatures which are actually given in the question. Is this one clear? Now let me read the statement of the question, and what are the key data which are given in the statement, that also we will note down. In a simple absorption refrigeration system as shown in the figure, the conditions at various state points are shown in the table. Okay, now we have to show all the state points on enthalpy composition diagram, HX diagram. How many of you are having HX diagram? Do you have printed copy of HX diagram? You should bring the printed copy of HX diagram, because I already announced that we will be doing numerical problems, so you should bring the copy. Okay. So on this printed copy of HX diagram, we have to represent all the state points. After that, we have to determine mass flow rate through the evaporator. So first part which we need to calculate is mass flow rate through evaporator. Then mass flow rate of weak and strong solution. Mass flow rate of weak and strong solution. And these we need to calculate if my refrigeration capacity is 1 ton of refrigeration. Okay. So refrigeration effect is given equal to 1 TR, 1 ton of refrigeration. Okay. And we also need to determine the heat transfer rate through absorber, generator and condenser. So it means that I need to calculate QA, QE, sorry, QE is already given, QC and QG. So all these three parameters also I need to calculate. After that, it is given in the question, check the energy balance. Check the energy balance and calculate CO. Question is clear? One diagram is given. Corresponding to that diagram, different state points are given. For the state points, values of pressure and temperature is provided. And other than that, it is mentioned that capacity of the system is 1 ton of refrigeration. For 1 ton of refrigeration capacity, we have to determine mass flow rate through evaporator, mass flow rate of weak and strong solution. Then we also need to calculate QA, QC, QG. Okay, and we need to establish whether energy balance is being satisfied or not, and then we need to also calculate the CO of the system. Anyone is having any doubt about this? All are clear with this? Okay, so shall we start? What will be our first task? We need to designate all the state points on the enthalpy composition diagram. Let's start with state point 1. What is state point 1? Inlet to the pump. Okay, so inlet to the pump, whether it is saturated or not, that we will be deciding now. But it's a liquid, that part is correct. Okay, because typically in the absorber what happens? Ammonia vapor get absorbed in the water, and then whatever the ammonia plus water liquid is, that liquid is actually taken by the pump, and in the top I am having vapors. Okay, so let's see. State 1 is having pressure of 1.75 bar and temperature of 25 degrees Celsius. Can you locate this point? So if I go to enthalpy composition diagram, this is H, this is X. First point is pressure is given 1.75 bar. Okay, and we know that at state 1 it is nothing but inlet to the pump. At inlet to the pump I will be mostly in the liquid region. So I will be referring to saturated liquid line. First I will be referring to saturated liquid line. So what is the pressure given? 1. So I will go to the saturated liquid curve and I will locate pressure of 1.75 bar. This is the line having pressure 1.75 bar. All of you have located? Please tell me. All of you have located? Now on this line, other data is that temperature is 25 degrees Celsius. Okay, so on the HX diagram you have these dashed lines, multiple dashed lines. Are you able to locate a line at 25 degrees Celsius which is crossing this pressure of 1.75 bar? Please tell me. 25 degrees Celsius line, is it crossing 1.75 bar? Crossing? Check it, quickly check. Is it crossing or not? Crossing? Okay. So somewhere over here I can see that 25 degrees Celsius and 1.75 bar are crossing each other, and this is the point of intersection. Okay. So the point of intersection will be nothing but my state number. It will be state 1. Anyone is having any doubt? This is state 1. Now at 25 degrees Celsius what is happening? Please tell me. It is crossing 1.75 bar line. So it means it is state 1 is nothing but a saturated liquid state. So one additional information we got from the table that it is a saturated liquid state because it is lying on the saturated part. All of you got this point? Now can you tell me at this point what is our enthalpy? How much is enthalpy? H1. On this point, whatever the value I will be getting on y-axis, that will be h1, and whatever the value I will be getting on x-axis, that will be x1. Okay. So what is the value of h1 for this case? Did you calculate? And also tell me x1. How much is h1 and x1? Please tell me. Minus 115. Are you getting this value or not? See, mobile phone you will not be able to see. You have to get the paper. H1 is minus 115 kilojoule per kg. All of you have got this or not? And what about X1? 0.393. 0.39. Okay. So H1 and X1 we have calculated.
So the diagram में तो approximate value निकल के है. Sir इसमें minus 115 gap है. तो इस टाइम पता है कि negative आ रहा है. कैसे निकालें?
You can calculate. How you can calculate?
Scale.
With scale, you have to designate and then you have to do the subdivision. You can calculate. Okay. But it should be on paper. If you are trying to do it on mobile phone, that's okay, no problem. Okay. Are you fine with H1 and X1? All have located. Now let's go to state 2. Now see, where is state 2? What is state 2? Exit of generator. At the exit of generator, generally from the bottom, what we collect? From the bottom we collect liquid. And state 3 is also exit of generator, but it is at the top. So from the top, generally what we collect? Vapor. So it means it is some rough estimate we have that state 2 will be close to the liquid, saturated liquid state, and state 3 will be close to the saturated vapor state. Not close to, but exactly the saturated liquid and saturated vapor. Why? Because in the generator, I am doing the heating process, and because of heating process, this liquid is actually evaporating. So it means I am in the two-phase regime. Within the generator, I am in the two-phase regime, and also generator is nothing but a vessel. Okay. So in the vessel, at the bottom, I will be having the collection of liquid. At the top, I will be having collection of the vapor. Vapor at the top will be pointing to the saturated vapor state. Liquid at the bottom will be pointing to saturated liquid state. Okay. So it means first idea from the basic understanding of the phenomenon and the process I have come to know is that state 2 will be my saturated liquid state and state 3 will be my saturated vapor state. Anyone is having any doubt about this? Because this information from basic understanding of the process you have to infer. Is this point clear? All are agreeing to this point? Okay. Now let's see the conditions. Now you can see what is given. State 2, pressure is 13.5 and temperature is 100. So both are same because it is in the two-phase regime. It has to be in the equilibrium state. Okay. So 2 will be my saturated liquid and 3 will be my saturated vapor. But pressure is now 13.5 bar and temperature is 100 degree Celsius. Okay. So now come back to HX diagram. What I need to locate now, please tell me. 13.5 bar. So say this is my line of 13.5 bar. And how much temperature? 100 degrees Celsius. Are you getting some point like this? X2 and are you able to look at point 2? Please tell me. Have you located point 2 or not? Exactly. Okay, fine. It would be slightly left of that because x1 is 0.39, x2 is 0.37. Almost close. Okay. Fine. All are able to locate? Okay. Now how to locate point 3? Okay, so if you have located H2 point 2, then you can calculate H2 and X2. Can you tell me what is H2 and X2? H2 is equal to correct 220 kilojoule per kg. And X2 is 0.37. Okay. Now, how to locate point 3? Please tell me. First, I need to refer to line, saturated vapor line with pressure of 13.5 bar. Then, I also need to refer equilibrium construction line corresponding to, this is my equilibrium construction line corresponding to 13.5 bar. Correct? Anyone is having any doubt? After equilibrium construction line, I need to obtain the 100 degrees Celsius temperature on this. How I have to locate? First at 100 degrees Celsius and 13.5 bar in the saturated liquid state, I need to move vertically up and I need to cross up to the equilibrium construction line. After it is crossing equilibrium construction line, I need to draw a horizontal line, and this horizontal line where it is crossing the saturated vapor line, that will be by nothing but the 100 degrees Celsius. So this is state 3. This point will be having 100 degrees Celsius. Are you able to locate this or not? Do it. I will not tell you H3 and X3. You have to tell me. Corresponding to this, my value of X will be X3. See more carefully. How much is X3? 0.94. Correct. Exactly correct. X3 is 0.94. And what about H3? Correct. 1530. Okay. 1530 kilojoule per kg. All of you are done with this state 3? Anyone is having any doubt? Please tell me. Fine. State 3, have you got 0.94 and 1530? Please bring always print out so that you can practice question in the class itself. At least one question in the class itself, and then you can try it. Okay, now we have to go to state 4, 5 and 6. There is one very specific feature about 0.4, 5 and 6. Can you identify after looking into the schematic? At state 3, I am having some composition, okay, and that same substance is going through condenser, expansion device and evaporator. From 3 to 6, I do not have anything where I can add ammonia or remove ammonia, or I can add water or remove water. So it means that overall mixture composition at 3, 4, 5 and 6 will remain. So whatever is my X3, same will be equal to X4, X5, X6. Is this point clear? The simple meaning of this is my line X3 on enthalpy composition diagram. Please see, this is X3. And if composition is remaining constant, 0.4, 5 and 6 must lie on this vertical line. Is this point clear? Anyone is having any doubt? 0.4, 5 and 6 will be lying only on the vertical line. Okay, now let's go to state point 4. State point 4 is exit of condenser. Okay, and 4 is having data 13.5 bar and 40 degrees Celsius. First point is, if I am referring to an ideal cycle, in an ideal cycle, always the exit of condenser is nothing but a saturated liquid state. Okay, so from my fundamental understanding for an ideal cycle, state point 4 should be a saturated liquid state. Is this one clear? And moreover, I can also calculate this. So what is pressure? 13.5 bar and temperature is 40 degrees Celsius. Okay, so what I need to do now, at 13.5 bar, I need to draw 40 degrees Celsius line, and that 40 degrees Celsius line must cross at same composition. Is this one clear? So in this case, if I assume my condenser is ideal condenser, then one data is redundant. Basically, temperature data is redundant over here, because for saturated state in a mixture, only two properties can specify. So one property I was knowing composition, other property I was knowing pressure. So that would have served the purpose. Okay. But third data, why it is given? Because whenever we operate the practical condenser, in case of practical condenser, it may so happen that instead of saturated liquid state at the exit, I am having subcooled state. Okay, so when I will be having subcooled state, temperature will be say close to 30 degrees Celsius. So if I draw if this is my 40 degrees Celsius line, if I draw a 40 degrees Celsius line, of course that will be going something like this. Now you can see 30 degrees Celsius and 13.5 bar is crossing at this point. But at this point, composition is not equal to 0.94. So it means this cannot be the state. Then the state at which temperature is 30, pressure is 13.5 and temperature and composition is X3. will be nothing but this state. And for a pressure of 13.5, because it is lying below the saturated liquid line, it will be nothing but a subcooled state. What my point? For an ideal situation, all 3 points should join, but temperature and composition will be useful in case my substance is subcooled in the condenser. Because for subcooled state, then the state will not lie on the pressure line, but it will lie below the pressure line. All are clear with this point? Because after doing this numerical problem, I will give you one variant of the same question where you have to solve it up to the subcooled state. So that concept now itself I have explained. All are clear with this point or not? Please tell me, because these are important concepts. Okay, so are we able to locate state 4? This is my state 4. What is H4? X is already frozen. Only thing I need to calculate is H4. One 125 kilojoule per kg. Okay, and you see, interestingly, one can also give you the question that if state 4 is a saturated state and only pressure and composition are known, can you determine what is its temperature? Of course, if you know this point, then you can determine what is the line passing through the. Okay, so temperature you can locate as well. So temperature at present it's a redundant data. Okay. Let's go to state 5. What is state 5? What is process 4 to 5? First go there. What is process 4 to 5? Expansion. Okay. So it means that from 4 to 5, I will be having decrease in pressure. But enthalpy will remain same. Composition is remaining same. So it means state point 4 and state point 5 will be, because enthalpy and composition are same. So 4 and 5 must lie on the same point. Okay, so H4 will be equal to H5. However, let's see what is given in the table. In the table it is given that at state point 5, pressure is how much? 1.75. What it means? This is 1.75 saturated liquid line. For 1.75 bar pressure, 0.5 is lying above the saturated liquid line. It means state 5 is in the liquid plus vapor. Got my point or not? In the previous class, just I explained the concept of throttle. This is a throttling process. Okay. So in the throttling process, state point remains the same, but pressure decreases. So if pressure decreases from this pressure to this pressure, then for this it is the saturated liquid line. If you are going above saturated liquid line, it will be nothing but a liquid plus vapor state. It will be the two-phase result. Okay. So one interesting fact we have come to know that state 5 is nothing but liquid plus vapor. Anyone is having any doubt about this? Please tell me. Do you have any doubt about this? If in the question the temperature was given even for 5, but I intentionally removed it. Okay. The reason for removing is because again this is a redundant data. You can calculate the temperature. How you can calculate the temperature? Can you tell me? This is 1.75 bar. I will be having some saturated vapor line also for 1.75 bar. Okay. If I keep on drawing multiple isotherms, the isotherm which will be passing through state point 5, that will be giving me the value of temperature at state point. What my point? This is my state point 5 and it is in the liquid vapor region. So this is my saturated liquid for 1.75 bar. This is saturated vapor for 1.75 bar. I know in between liquid and vapor my isotherms generally follow this type of trend. Okay. Is this one clear? Inclined line represents the isotherm. So from different points on 1.75 bar I can draw multiple isotherms. There will be one isotherm which will be coincident to point number 5. The isotherm which is coincident to point number 5 and starting at this point corresponding to this whatever temperature I will be having, same will be the temperature of state point 5. Anyone is having any doubt about this? Okay, let's go to state 6. What is state 6? Exit of evaporator. What are the conditions given? First point we must know, exit of evaporator should be close to the vapor region. Either it should be pure saturated vapor or it could be mixture of liquid plus vapor but with very small amount of liquid. Because in the evaporator once it has taken the heat, it will be converting into liquid plus vapor phase. Is this point clear or not? Please tell me. All are clear to this point? Yes. So now can you tell me how to locate 1.75 and 0? What I will be doing? At 1.75 bar pressure, at 1.75 bar pressure, I will be drawing an what? Isotherm. Please tell me. Am I correct? How to locate state 6? How to locate state 6? What are the conditions? Pressure is 1.75 bar, temperature is 0 degree Celsius and composition is 0.94. Okay. But it could be either in the saturated vapor or it could be the liquid plus vapor state because it will be close to this. So what I need to do? In order to determine, I must draw an isotherm. Okay. So for 1.75 bar and 0 degree Celsius, let us consider this is my 0 degree Celsius. Okay. This is the point on saturated liquid state. From this point, what I need to do now? I need to go to auxiliary line or equilibrium. Auxiliary line corresponding to 1.75 bar. Okay. From this, I will be drawing a horizontal line. This horizontal line is crossing at this point the saturated vapor line. So it means this temperature will also be 0. Now I will draw a straight line in between these 2 points. This is my temperature of what? 0 degree Celsius. Now where, and this is at which pressure? 1.75 bar. And third property is composition, which is 0.94. Where all these three are meeting, that is my point 6. What my point? What is X6? Please tell me. Vivek, and what is X6? Is this problem interesting? What is X6? X6 is one is correct. First digit is correct. Huh? No, no. 1200. You are closer. 1099.15. This you have calculated graphically. This can also be calculated analytically. Shall I explain or leave it? You want to understand analytical formulation for this, or this is enough? Okay. Okay, so this is 0.6. Okay. Now this is an isotherm. It is crossing at saturated liquid point at this. So this will be my state 6F and this will be my state 6G. Is this part clear?
X6 graphically
Sorry?
1250 के आसपास
That is graphical because you are not drawing with proper scale and all. So it's okay, don't worry. 1250 is closer. But if you follow analytical method, you will be able to calculate exactly. Okay, so let me explain, quickly see this also. Time is less. Do you have class at 9? No. You have, those who have, they can leave, they can refer to recording. Okay, I'll complete this problem. Okay, so this is my state 6. At 6, the vapor state will be 6G. This will be on saturated vapor line and liquid state will be 6F. All are clear with this point? At 0.6, I know that I am having mixture of liquid plus vapor. Okay. So let me assume that if I assume my mixture mass to be 1 kg, in 1 kg mixture mass, I have W6 amount of liquid. Is this point clear? Then how much vapor I will be having? 1 minus W6. Is this point clear? So 1 kg I am having the total mixture. W6 I assumed amount of liquid. 1 minus W6 I will be having amount of vapor. Also one additional thing, I know that at state 6 I am having X6 as the composition. This is whose composition? Ammonia's composition. 0.94 means 94% ammonia and 6% water. Okay. So if I write mass balance for ammonia, mass balance for ammonia will be 0.94 into 1. That is the mass of ammonia in 1 kg. 94% ammonia means 0.94 is ammonia. And in this ammonia, some ammonia will be in the liquid state, some ammonia will be in the vapor state. How much ammonia will be in liquid state? W6 into, please tell me, W6 into W6 into something plus 1 minus W6 into something. Whenever you have a mixture, then liquid is having different composition, vapor is having different composition. What is the composition of the liquid? Corresponding to 6F. And what will be the composition of the vapor? Corresponding to 6G. Tell me, what are the values of 6F and 6G?
0.5.
Correct. 0.57. And XG? 995. Okay. So, the point is, in this 1 kg mixture, because it is a mixture of liquid and vapor. Okay. So, this mixture, if I see this mixture at these isotherms, liquid will be corresponding to saturated liquid point, vapor will be corresponding to saturated vapor point. So if I refer to composition of liquid, which is X6F, X6F comes out to be 0.57. It means 57% is ammonia in the liquid phase. So if W6 is the liquid amount, then total amount of ammonia in this liquid will be 0.57 into W6. Correct? And X6G is basically 0.995. It means 99.5% in the vapor is of ammonia. So this is my total vapor mass multiplied by composition of ammonia will be giving me the total mass conservation for ammonia. Correct? From this, how much is W6? 0.129. Let me see. Yes, correct. 0.13. So 0.13 is W6. Now, in the mixture, I know that 0.13 fraction is of liquid and 1 minus 0.13 fraction is of vapor. So if I know the, what is this? This is nothing but liquid fraction. If I need to calculate dryness fraction, how much will be dryness fraction? What is dryness fraction? Fraction of vapor, 1 minus W6, 87. Okay. Once I know the dryness fraction, calculating enthalpy is easy. What is the enthalpy formula? Amount of liquid into enthalpy of liquid. Amount of liquid is W6. Enthalpy of liquid will be H6F plus amount of vapor, which is 1 minus W6 into enthalpy of vapor, which is H6G. H6F and H6G are easy to calculate because these are only lying on the saturated state. What are H6F and H6G? H6F is how much? Minus 245, correct? H6G. Please tell me. You are always saying either little bit over predicted or under predicted. Badal. 1300. Okay. So if you substitute these values, you will be getting 1099 points. So alternate method is there, but for alternate method you have to calculate manually. Easy to. But isotherm still you need to draw because that saturated vapor point you need to catch 6G. So for 6G at least isotherm you need to draw. Alternative approach is clear to you? Okay. I think we have done all the enthalpies. Now let's refer to questions. What is first part?
Mass flow rate.
What will be mass flow rate of refrigerant? In the evaporator, change in enthalpy is from
Is 5 to 6.
5 to 6. So mass flow rate through the evaporator will be how much? Refrigeration effect divided by H6 minus H5. Refrigeration effect is 1 ton of refrigeration. Calculate it. How much it is?
0.0036.
Is it correct? All of you have got this value? Now what is next? Next is mass flow rate of strong and weak solution. What do you mean by strong and weak solution?
The concentration of ammonia.
Yes. So if you see, this is nothing but strong solution, because here concentration of ammonia is more and here concentration of ammonia is less. So this will be nothing but weak solution. All of you are clear? At state 3, what is our aim? To remove water so that we can extract pure ammonia. So pure ammonia we are supplying to condenser, almost pure ammonia in this case, not exactly because concentration is not 1. Okay. All are clear with this or not? So please, those who have class, they can leave. And you can follow the lecture through recording, okay? Is this one clear? Now, okay, in absorber, if I apply mass balance, what will be happening? This is state 2. You can see over here, this is state 2. Some mass is coming at state 2 into the absorber. Some mass is coming at state 6 into the absorber and leaving at 1. So I can simply write that m dot 6 plus m dot 2 will be equal to m dot 1. Okay. In the similar way, I can apply this balance for composition as well. So from here I can write m dot 6 into x6 plus m dot 2 into x2 equal to m dot 1 into x1. Okay. I have two equations, two unknown. What are unknown? M dot 1 and M dot 2. These two are unknowns. Okay. So if I apply these equations, can you tell me what I will be getting? How much is M dot 2? From these two equations, because I have two unknowns, two equations, if you solve for M dot 2, you will be getting m dot 6 into x6 minus x1 divided by x1 minus x2, and it comes out to be 8.58 into 10 to power minus 2. And m dot 1, if you calculate, it comes out to be m dot 6 into x6 minus x2 divided by x1 minus x2.
Sir,
8.95. Yes, tell me. Correct? So these I have calculated the mass flow rates. Now what I need to do, I need to calculate all the heats in absorber, condenser and generator. Evaporator already we know 1 ton of refrigeration. Okay. So how to calculate heat in the absorber? No. Because across the absorber, if you apply enthalpy, then there is one more unknown. QA. QA is also. Okay. So that's why enthalpy will not work. Okay. Now we need to apply enthalpy equation, energy balance equation. So if I apply energy balance across absorber, what I will be getting? And in this case, m dot 6 was nothing but equal to m dot E. Okay. So enthalpy balance will be m dot 6 into H6 plus m dot 2 into H2 equal to m dot 1 into H1 plus Q dot A or QA simply. So from here, how much is QA? Please tell me numbers. How much is QA? Calculated? 33.14 kilowatt. Okay. Now let us apply energy balance across generator. What will be energy balance across generator? Please tell me. In generator 2 and 3 are going out. Okay. So m dot 2 is going with what? H2. M dot 3 is going with H3. Okay. What is coming in? 2 dash. So M2 dash into H2 dash, and what else is coming in? QG. Now m dot 3 has to be equal to m dot E, because ultimately whatever is going into condenser same is in the evaporator. M dot 3 is m dot E. Now let us assume pump work is negligible. If pump work is negligible, then H2 dash will be equal to H1.
Yes.
Pump work is H2 dash minus H1. So pump work is negligible, it means H2 dash is equal to 1. Okay. Now after this, what I will be getting? And M2 dash is nothing but equal to M1 dot. Okay. M2 dash is M1 dot. Tell me how much is QG? Quickly tell me.
$34.7.
34.70 kilowatt. Yes. Next is heat reacted in the condenser. Very simple. M dot 3 into H3 minus H4. How much it is? 5.07. 10 to the power minus 3 mass flow rate. Okay. 5.07 kilowatt. Now what I need to do, I need to check energy balance. How to check energy balance? Heat added is QE plus QG. That must be, if pump work is negligible, this must be equal to QA plus QG. Sorry, QA plus QC. Now check. This I am getting 38.22 kilowatt, and other one I am getting 38.22 kilowatt if rounded off to 2 digits. Are you getting or not? 33 and 5 is 38, and 1 plus 3.51 plus 34 is 38. So it means energy balance is satisfied. Okay. What next? COP. What is COP? QE divided by QG. Okay. Now let me write next variant of this problem which you have to solve by your own. I am writing the complete statement. Suppose a preheating heat exchanger is added to the system of previous problem such that the strong solution leaves it at 40 degrees Celsius. Determine heat transfer rates through various components and this COP. Have you got the question? What is question?
State 340 degree.
Sorry? No.
State 2 dash 40 degree.
Yes, correct. That is also strong solution. Shall I draw the system? The only difference is, let me show you. This is your generator. Here state 3 is leaving. Here state 2 is leaving. But when state 2 is leaving, before the expansion there is preheater. Then there is expansion, and here whatever is coming from the pump, that is first passed through the heat exchanger and then added to the generator. So it means this is 1 dash and this is my preheater. So the strong solution in preheater, which one is weak, which one is strong? In preheater, this is
1 dash is strong.
weak and this is strong. Okay, and strong solution is leaving at, so T1 dash is additional information has come. Now you have to write energy balance here also. That will be governing what enthalpy is going into the absorption. Do this, calculate all the heat balances and COP. You will be finding that COP will be significantly improving. Why? Because this heat we are using for preheating, so we need to now add less heat in the generator. QG will be decreasing. Okay, so COP should increase. Try this. Okay, try this, and in the next class, tell me what is the value of COP, because tomorrow is holiday. You will be coming only on now directly Monday. So on Monday you should tell me what is the. Okay. Shall I give you one more variant? You want to try? Then let me give you one more variant. Today we have lot of time. Let me give you one more variant. If a subcooling heat exchanger is, already I explained you the concept of subcooling, is included in the previous problem, and it is assumed that the vapor at the exit of heat exchanger is saturated vapor at 1.75 bar. Find the mass flow rates, heat transfer rates, and COP. Let me draw the system, because the system will be a bit more complicated. QG, QA, this is subcooling heat exchanger, and this is of course preheating heat exchanger. So it is saying that, read the statement. Vapor at the exit of heat exchanger is saturated vapor. So it means earlier whatever was leaving the evaporator, that was not saturated Now when after heat exchange, here it is saturated with. In this case, because you are doing subcooling, specific refrigeration effect will increase, so it will be further giving you the improved CO. Okay, you have lot of time till Monday. Solve all these two variants. If you are able to solve these, you can solve any problem on vapor absorption. Okay, so all of you please solve these problems, and also ask all your other friends also to solve.